Okay, thank you. So the title of this work is Estimating Approximate Incentive Compatibility, and it's joint work with Nina Balkan and Tuomas Sandholm. So we're all here familiar with incentive compatibility. It's a fundamental concept in mechanism design. And a mechanism is incentive compatible if the agents will maximize their utilities by reporting their types truthfully. So despite all the nice properties of incentive-compatible mechanisms, many real-world mechanisms are not incentive-compatible. So these include, for example, discriminatory auctions, which are basically a multi-unit variant of the first price auction. They're not incentive-compatible, yet they've been used to sell treasury bills in the United States since 1929. And they're also used to sell electricity in the United Kingdom. Another example of a non-incentive compatible mechanism is, of course, the generalized second price auction, which is used for sponsored search auctions. Moreover, nearly all fielded multi-item, multi-agent, or combinatorial auctions are not incentive compatible. So one example that my collaborator Tuomas has worked a lot with are sourcing auctions, which is the way that large companies like Procter & Gamble obtain the goods and services they need to run their operations. And then one other mechanism that, that Kira talked about yesterday are uniform price auctions, and those, as we talked about, are not incentive compatible. So why aren't real-world mechanisms incentive compatible? There's a lot of reasons for this, but here's just a few. For one, it can be expensive for agents to compute their true values, especially in combinatorial domains when there might be an exponential number of bundles. So a mechanism that would be incentive compatible if the agents could actually compute their true values is no longer incentive compatible. Another reason is that for whatever reason, oftentimes non-incentive compatible mechanisms have rules that are easier to explain. So one example of this is the first price auction, which is pretty much the simplest auction you could hope to explain to someone. Oftentimes, especially in electronic commerce, the bids from previous auctions are used to tune the parameters of future auctions. So an agent might be strategic now in order to get higher utility, hopefully, in the future. Auctions might leak agents' private values, so they might not want to actually reveal those private values. And finally, agents might not actually be risk neutral. So an auction that is incentive compatible for risk neutral agents is no longer incentive compatible. So due to the ubiquity of manipulable mechanisms, many researchers have looked into relaxations of incentive compatibility, or approximate incentive compatibility. So at a high level, a mechanism is gamma incentive compatible if, for each agent I, if everyone except that agent is truthful, she can only increase her expected utility by a factor of gamma when she lies about her type. And there's a lot of different variations on approximate incentive compatibility. This is just one of them. And this kind of flavor of approximate incentive compatibility has been studied by many different people in the EC community especially. So in this work, our overriding goal is, given samples from the distribution over agents' types, we want to estimate this incentive compatibility approximation factor gamma using these samples. And I'm going to make this more formal in a few slides, but this is the high-level goal. And this complements Nina's talk this morning about the literature on mechanism design via machine learning or sample-based mechanism design. So these are related topics, but non-overlapping. So why might you want to estimate this incentive compatibility approximation factor? Well, some mechanisms might have a terrible worst case approximation, incentive compatibility approximation factor, worst case over the distribution over agents types, but they may be nearly incentive compatible for the specific distribution at hand. So you can use a mechanism that you may have discarded as non-incentive compatible, remaining optimistic that the agents will be truthful. Another reason why you might care to estimate this incentive compatibility approximation factor is in the context of mechanism designed via machine learning. So there's been a recent development of work that has been looking at designing mechanisms using machine learning, and in particular using deep learning. So there, your machine learning objective function is to maximize revenue over your training set, and you have a constraint requiring that this estimate of incentive compatibility over the training set is small. So there's been a few works that have looked at this mechanism designed via deep learning. So you know that on average over your training set, your mechanism is incentive compatible, but you might want to know, is the resulting mechanism actually going to be incentive compatible or nearly incentive compatible? Okay, so now I'm just going to go over a little more background, and I'm going to make our goal a little more formal. So in this work, there are n agents, and the type space is going to be the hypercube in m dimensions. And we're going to make a standard assumption that we see all the time, which is that the agents' types are drawn from some probability distribution. So in particular, there are n agents, so T1 is the type of agent 1, Tn is the type of agent n, and this tuple of types is drawn from a distribution D. And this distribution D is unknown, like in Nina's talk. So in this talk, we're going to require that D is a product distribution. So for each agent I, there's a distribution Di, and their type Ti is drawn from Di. And the distribution over types is the Cartesian product of these n distributions. I'm going to use the notation D minus I to denote the distribution over all agents types minus agent I. And we relax the assumption that the underlying distribution is a product distribution in the paper, but for simplicity, I'm going to make this assumption in this talk. Okay, so now I'm going to a little more formally define incentive compatibility. So an auction is incentive compatible if for any agent I, in expectation over the other agents' types, their utility is maximized by reporting their type truthfully, so long as all the other agents are also truthful. So the utility of agent I, I'm going to denote it as this function u, where Ti is agent I's true type, Ti tilde is their reported type, and T minus I is the other agent's types. And we're assuming that they report truthfully in this definition of incentive compatible. So a mechanism is incentive compatible mathematically now if for each agent I, any true type Ti and any reported type Ti tilde, their expected utility from reporting truthfully, so an expectation over the other agent's bids from reporting truthfully, is at least their utility from reporting strategically with a type of Ti tilde. And you might recognize this as the ex interim notion of incentive compatibility. We also look at ex ante in the paper, but I'm just going to focus on ex interim in this talk. So now moving on to approximate incentive compatibility. An auction is gamma incentive compatible if for every agent I, any true type Ti they might report, any true type they might have, any reported type Ti tilde, their expected utility from reporting truthfully is at least their expected utility from reporting with a type of Ti tilde minus this additive factor of gamma. And again, this kind of flavor of approximate incentive compatibility has been studied pretty extensively. And like I said, our goal is to estimate this incentive compatibility approximation factor gamma using samples from the distribution over agents types D.
So are you looking for the expected value of gamma, or
we're looking, yeah. So we want to be, I'll make this more formal, but we're going to want to find gamma hat. We're going to find an estimate gamma hat such that with high probability over the draw of the samples, gamma minus gamma hat is smaller than some epsilon. Does that make sense?
But gamma will be distributed when Ti is distributed, right?
Yes. So it's worst case over Ti and Ti tilde. Yeah. Yeah, thanks for the question. Okay, so now I'm going to get to our estimate, but I'm going to start off with a first try, which isn't going to work. So the first thing you might try is to measure this gamma by measuring the maximum utility any agent I can gain by misreporting her type on average over samples. Okay, so this T minus I1 is a sample from the distribution over the other agent's types minus agent I. So T minus I1 up through T minus IN are n different samples from this distribution over the agent's types. So mathematically, the first thing you might try is take the maximum over all types Ti, reported types Ti tilde, of the average amount the agent could gain from reporting a type of Ti tilde minus reporting their type truthfully.
There's no J in the sum.
The J is in the, we're summing over the samples, so the J is in the superscript there. Yeah. Okay. So the problem with this approach is that these utility functions, as I'm going to illustrate in a couple of slides, are non-convex. They have many jump discontinuities. So it's not clear that you can even compute this maximum value in finite time. So instead, what our estimate is, our estimate gamma hat, is instead going to be the maximum utility agent I can gain by misreporting her type, again, on average over these n samples, so long as her true and reported types are from the uniform grid G over the type space. So this uniform grid, since our type space is bounded, is going to be finite, so there is a finite time procedure. And mathematically, gamma hat is, again, it's just the same as before, but this time we're taking maximum overall true types, Ti, reported types, Ti tilde, from this uniform grid over the type space. And just to show this with a picture, maybe we have Ti going along the x-axis here, Ti tilde going over the y-axis here, so we're taking a uniform grid over the type space. And the key challenge here is that we miss miss pairs of true and reported types, which have large utility gains. So there might be true and reported types that kind of fall in between these grid points that we're totally missing out on by just searching over the grid. So the key question we want to answer is, what is the difference between the true incentive compatibility approximation factor gamma and our estimate gamma hat? The mechanism is going to show up. It's going to play a big part in answering this question. Yeah. Okay. So the key challenge in using this uniform grid approach is that these utility functions are volatile. So let's just think, for example, of the first price auction, where, of course, the highest bidder wins and pays their bid. So let's think about varying the bid Ti tilde along the x-axis. Just a second. Okay, so we vary the bid Ti tilde along the x-axis, and we're measuring utility of the first price auction along the y-axis. And this is for a fixed true type, Ti, and a fixed true types of the other bidders. And all we're varying is the bid of agent I. So let's imagine that the maximum competing bid, so the largest component of this vector T minus I, falls here. So when the agent's bid, Ti tilde, is smaller than this maximum competing bid, agent I is not going to win. They're not going to pay anything, so their utility is just going to be 0. When their bid is larger than this maximum competing bid, they're going to win, and their utility is going to be their value minus their bid, so utility is just a decreasing function of their bid. Okay, so the volatility of these utility functions is only exacerbated when we're looking at average utility over a set of samples. Because here, for example, if we have 4 samples, and each of the maximum competing bids falls at one of these 4 lines, we're going to have many more jump discontinuities, 1 per sample. And just for example, if we were to measure agent I's utility as a function of their bid using some grid, for example, these blue dots, we could totally miss out on the interesting portions of this utility function. We might think that their utility is just 0 no matter what their bid is. So this raises the question, when is this distribution over agents' types actually nice enough that we can use the uniform grid and get good utility estimates? And to answer this question, I'm going to rely on a notion called dispersion. So functions f1 up through fn, let's say that they map Rm to R, are wk dispersed if every W ball in the domain contains discontinuities of at most k of the functions. And this is something that dispersion is a notion that Nina and I and another student, Travis Stick, introduced in a different context last year. So just to illustrate this pictorially, let's imagine plotting the sum of these functions. If the functions are not dispersed, then there's some interval that contains many of the function's discontinuities. But if they are dispersed, then for every interval in their domain, that interval contains few discontinuities. So this kind of takes care of the, if our utility functions are well dispersed, this kind of takes care of this issue of a lot of discontinuities falling in some interval and the utility functions being very volatile. Okay, so with this notion of dispersion, I'm going to describe our guarantees. And I'm going to remind you first of what our estimate gamma hat is. So remember, it's the maximum utility agent I can gain by misreporting her type on average over these samples drawn from the distribution over the other agent's types, so long as her true and reported types are a part of this uniform grid. So here's what our theorem is, our main theorem is, and this is just an informal version. I'm not going to give the formal version in this talk. So informally, if the utility functions induced by these n samples are piecewise Lipschitz and wk dispersed, which just means that not too many discontinuities fall within some ball of their domain, then we can successfully estimate this gamma hat using the W grid. So just the uniform grid over the type space with edge length W. And our guarantee is that with high probability, the difference between gamma hat, our estimate, and gamma, the true incentive compatibility approximation factor, is at most LW, where L is the Lipschitzness factor of these utility functions. W and K are the dispersion parameters. So LW plus K over N. N is the number of samples, plus square root of D over N. Okay. D is just a standard machine learning measure of these utility functions' intrinsic complexity. And this D is going to depend on the specific mechanisms that we're looking at. I'm not going to define it exactly, but it's basically like pseudo-dimension, which we saw earlier in Nina's talk today. And I just want to give you an idea of what this proof looks like in two bullet points. So if you imagine looking at a reported type and a true type, if you snap that reported and true type to a point on this uniform grid, by dispersion, the utility is only going to change, the average utility is only going to change by a factor of LW plus K divided by N. And this follows from just dispersion. It's a simple lemma based on dispersion. Next, since we don't actually know the distributions over agents types, we're just sampling from this distribution, we're going to incur another square root of d over n additional error from sampling. And perhaps the square root of d over n term looks familiar from Nina's talk today. So when is, oh, yep.
So for example, if k is equal 5,
yeah.
It might be that you sample with a grid of w.
Yep.
There might be some small part which is infinity and you just miss it.
Yeah, so
You actually need to sample w over k or w over k squared, no? Because you might miss a tiny part that goes to infinity.
So the utility functions, I am assuming, are bounded because the agent's types are in the hypercube. The utility function is bounded, so that infinity jump shouldn't be a problem. And the Lipschitzness factor also helps take care of this too. But thanks for the question. Okay. So when is this guarantee actually good? So if W is basically like 1 over square root of n, n is the number of samples, and k is about square root of n, then our estimation error is going to go to 0 as the number of samples grows. And we prove that these WK values of 1 over square root of n and square root of n hold so long as the distribution over agents types is sufficiently nice. And I'm going to give a few examples now. So when does dispersion hold? Let's say that the agent's types has a density function whose range is bounded between 0 and kappa. So this is just saying that there aren't any like point masses in this distribution over agents types. Then let's think about the first price auction. And the first price auction is increasingly being used by companies for auctioning off, for example, display ads. So we prove that so long as this niceness property holds, the kappa niceness property holds, then the R estimates error is going to be bounded by the number of agents plus 1 over kappa, that niceness parameter, divided by square root of the number of samples. And in the paper, we also look at combinatorial first price auction. Moving on to generalized second price auctions, which are again used for these sponsored search auctions, we show that the R estimates error is pretty much the same as for the first price auction, except now the number of agents is raised to the 3/2. We look at the discriminatory and uniform price auctions, which are basically just like the first price auction, but for multiple units. And here our estimates error is number of agents times the number of units squared plus 1 over kappa divided by square root of the number of samples. So just to wrap up, in this work, we provide techniques for estimating how far a mechanism is from incentive compatible. To do so, we introduce an empirical variant of approximate incentive compatibility, and we bound our estimates error using this notion of dispersion. We provide guarantees for the first price auction, a generalized second price auction, discriminatory auction, uniform price auction, and an auction I didn't talk about, which is the second price auction under spiteful agents. And just in the interest of time, I think I'll skip the future directions and take any questions if there are any. Thank you.
Any questions?
Yep.
So I may ask an obvious question, but have you looked at non-uniform grids, where when you can make the grid somewhat denser in more important areas that you may?
Yeah. So one thing that I didn't have time to talk about is we kind of look at two approaches for finding this finite subset to search over. One is this uniform grid, and the second is a more kind of classic learning theoretic cover from learning theory, which is kind of more along the lines of what you're talking about. But yeah, you could also think about maybe like continually searching, doing a more smart search in like specific areas that seem more promising, like you mentioned. We haven't looked at that specifically though. Yeah.
Are you sure that you really need the dispersion property? Because the Lipschitz is not enough. For example, in what you said, the first price auction, it's not Lipschitz, so it's not a counterexample actually. Yeah, because it's a jump from 0 directly.
Oh yeah, it just needs to be piecewise Lipschitz. So there are just going to be discontinuities, but when you're kind of in between two discontinuities, we require this Lipschitzness property. Yeah. Thank you.